Again, okay, good morning, and it's 11 a.m. and yeah, we can continue. The first homework, I haven't started grading. I will. Then second homework is already I posted, right? A preliminary deadline is also there in Blackboard. And yeah, I fixed the problem. You remember you complained at the very beginning that the Blackboard was almost invisible for you, right? So there was some issue, right? So IT people fixed that for me, right? So now it should be visible for everyone, right? Yeah, so the second homework is there. And of course, some of the problems, we haven't discussed some of the material which you will need to solve some of those problems. Okay, but anyway, back to our discussion. So where we are. You remember, at the very beginning, we laid down the foundation, right, of the Newtonian formalism. And then, as a first point, we went to a multi-particle system, right, when we basically adopted Newton's second law for a multi-particle system. As a result, all the internal forces got washed out and so on. Then we started thinking what can be used to make our life maybe somewhat easier if we want to describe a multi-particle system, right? And we started sort of wandering around over a multi-particle system, searching for something useful. And we ended up with some interesting point, the center of mass. We give a name as center of mass, right? And we actually gave two definitions. And today we're going to use one of those, right? The first definition is kind of useful from the point of view of understanding what the center of mass, but kind of completely useless in terms from the practical point of view. The second definition is kind of very practical, but not very useful in terms of understanding, right? So, but of course we use a practical definition. Right, so we introduced the center of mass, and then we spent pretty much the whole previous class just looking at all ways of finding the center of mass point, all the tricks, right? And we found the center of mass of a rigid object and so on. And at the end, we actually started looking what's the advantage or what are the beauties of having the center of mass in terms of description of the multi-particle system, description of motion of a multi-particle system, right? And that's where we ended up. So now let me quickly point the major, write the major points of the center of mass, and then we will continue from here. So the first one, again, we started from the definition. We differentiated it once, right? And after sort of massaging it a little bit, we ended up with this expression. Right, so we ended up that the total linear momentum of the multi-particle system equals to the total mass of the system times the velocity of the center of mass. So R, it's a position, R capital position of the center of mass. And I told you, wow, it's a first wow, right? Amazing feature that if you want to know the total linear momentum of the whole system, multi-particle system, you can do this. Basically, create a fake particle, right, with the total mass of the system, position it at the center of mass, find its velocity, m times velocity of the center of mass, and it's a total linear momentum of the system. So you don't have to chase each particle getting its linear momentum and then adding them all up. You just find velocity of the center of mass, multiply by the total mass of the system, and that's it. It's a tremendous simplification, right? It's a first amazing thing about the center of mass, right? So, and I will just write amazing, right? So that's the first. Right, and then we went deeper. We differentiated one more time in order to see what happens on that level. So we differentiated one more time with respect to time, and of course we applied, I think we applied here Newton's second law adopted or applied for a multi-particle system. And we ended up with this equation, and that's where we basically stopped. Right? Which way I wrote it? Okay, this way. So the total mass of this system, the acceleration of the center of mass equals to the net external force acting on the system. And that is the second wow, right? What's wow about this? Okay, effectively, it looks like Newton's second law applied for a point mass. Point mass of mass m, position of the center of mass, right? And all these forces acting on the center of, acting on that particle, fake particle m. Of course, in this case, it is a fake particle m. But this particle m doesn't exist, right? So how can this equation be used, right? Okay, so let me draw a couple of pictures quickly. So our goal was, or is, let's assume that this is our system. It can be a rigid object, it can be a multi-particle system. Okay, rigid object is a multi-particle system, right? Right, total mass m, right? And let's say net external force acting on this system is F external. It can consist of several, right? But let's assume that we added them up, and this is the net external force acting on the whole system. All forces added. Right, and our goal, you remember, we want to describe the motion of the system completely. We want to be like a fortune tellers predicting the future of the system. And, right, at least we want to get at least something. Right? Okay, and now we're getting this. It looks like if we find the center of mass, and we know we spent previous class, the whole class, of finding the center of masses, and now squeeze the whole system at the center of mass, creating basically fake particle, fake point mass with mass m capital, right? So this is the center of mass, right? And then, if we apply all these external forces on our fake particle, right? So that's our F external. Then, solving this equation, which is quite simple, right? Okay, so we can say theoretically it's possible to solve it, and it's not that complicated, right? So theoretically we should be able to solve the system. If you solve that system, you will get a trajectory of this fake particle. You will get a trajectory of the fake particle, right? So you will get this trajectory. And, of course, since our fake particle is positioned at the center of mass, this trajectory gives us trajectory of the center of mass of our system, which we want to describe. So exactly the same trajectory is here, right? Same trajectory. So it looks like this equation gives us some information about the motion of the system. Of course, you understand this description is not complete. So we're getting a partial description of the motion, right? So we're getting the motion trajectory of the center of mass. Okay, so we're getting some information about the motion of the system, right? And since it's something new, let's just give it a cool name to this motion, to this trajectory. And that is basically definition of translational motion. Motion of the center of mass, so solution of this equation, give us a translational motion. So the center of mass easily allows us to find the total linear momentum of the system, and also it allows us to find translational motion of the system. So let me write this down. So, right, and this can be called translation. I missed one letter. Called translational motion. And as I said, basically now we can use that as a definition of translational motion. Right. Of course, we all know that translational motion quite often is not enough, because we also have some kind of rotational motion, and we know it's usually about the center of mass, but right now we don't know that. That will be the next step. So for now, we introduced the center of mass, and naturally we came to the point, to this equation, and we naturally came to the translational motion. Again, which is partially described motion of the system. Not completely, but one step at a time. Right. So you see, okay, yeah, this center of mass happens to be already ridiculously useful. But of course, we will see even more advantages of having the center of mass in our disposal. Right. Okay, so that's basically some small piece which we haven't discussed in the previous class. And now, let me separate this. Right. Basically, we're exhausted this part. So we introduced, you remember, the linear momenta, right? The total linear momentum, Newton's second law for multi-particle system. We introduced the center of mass, and basically we extracted everything that we can out of the center of mass. So now this is done. So now, but we still know that this description of motion is not complete. Of course, we know there is some rotational motion. So now the goal is to dive into that part so that we can describe rotational motion of the system, right? How to do it? Of course, since linear momentum didn't lead us to that, so it means that we need to introduce a new set of tools, new quantities, right? So we need to start building now a small additional part of Newtonian formalism, right, in order to describe rotational motion, right? So now let me new section, so it's a 3.4, and let's introduce angular momentum, because again, as I said, linear momentum didn't lead us to rotational motion. So let's introduce new tools, right? Linear momentum, and of course, first we need to introduce it for a point mass, because all the new quantities, new ideas are usually introduced for point mass, and then we can apply that for a multi-particle system, for a rigid object, and so on. So linear, not linear, angular momentum. So let's introduce that. And I'm sure that during the history of physics, right, researchers tried to introduce tons of different quantities, right, hoping that they will be useful. And only a few of them survived. And of course, linear momentum survived because it happens to be ridiculously useful, right, and plus under certain conditions it is conserved. Angular momentum survived because, again, useful, and under certain conditions it will be conserved, right? So only a few of them survived, right? And so let's introduce. So let's assume that we have some point mass, mass m, velocity, v, and of course we can introduce the linear momentum. Let's say the linear momentum is, which way I label it? Just p. Just p. Linear momentum particle as linear momentum. So we want to describe it. Let's introduce some reference frame. Right. Let me position it somewhere over here, for example. Right, so y, x, and of course we can introduce a position vector. Right, so it will be r, right, which describes position. And so now let's try. Let's introduce a new quantity in this way. So L equals R cross P. Basically, I can put 3 lines by definition. So we introduce it. It's like at the very beginning, we introduce linear momentum. Out of the blue, let's try to use this quantity. Maybe it will be useful, right? And so now we're introducing this one. Right? And again, the difference, like at the very beginning, I asked you, remember, what's the difference between F equals MA and P equals MV? the difference is fundamental, global, because F equals ma. It's not just a formula, it's a universal law which is capable of describing motion of any system. And P equals mv is just a definition of linear momentum. Here the same, it's just a definition of angular momentum. That's it. Right. Of course, we can frame it, just a definition of angular momentum of a point mass. Okay, then I can ask, what's the major difference between linear momentum and angular momentum? Of course, you can tell me it's a stupid question because basically apples and oranges. How can you compare apples with oranges? But still, I want to compare because there is one important difference. Linear momentum does not depend, the value of the linear momentum does not depend on the choice of the origin. You can position origin anywhere you want and the linear momentum is going to be the same. But angular momentum, because of this, are sensitive to the choice of the origin, right? So basically, you can make L you can make L anywhere, anything. You can get any value of L. You can just grab the origin and keep moving, right? So you can make L bigger, you can make L smaller, or even if you position, for example, the origin along this line, right? For example, over here, right? O prime. And in that case, angular momentum will be even 0, right? So from one point of view, kind of it's nice because you have kind of freedom to make L, to give L any value, right? So sensitive to the choice of the origin, right? So that's what I wanted to remind. So L depends on a choice of origin. Oops. Or maybe on a position of origin, on a position of an origin. Right. So we need to remember that. And of course, in this case, so the angular momentum will be, okay, right-hand rule, of course, it will be angular momentum will be into the board, L into the board, right? So cross product, you can use right-hand rule, you can use determinant to find the value. Right? Okay, so that's the definition, and now let's look at the dynamics, because again we still don't see the beauty of introducing this angular momentum. Let's look at the rate of change of the angular momentum. So now let's look at dynamics. What happens in time? So we'll get, which way I wrote L dot? Yeah, let me just write L dot. You know what I don't like, it's overlapping with the letter above. So L dot equals, right, so it will be R dot cross P plus R cross P dot. Okay, first, R dot cross P, that is obviously 0 because P is MR dot. So we have, if you take a cross product of two parallel vectors, right, of course you will end up with 0, right? So that is 0. And now, over here, I will open my explanation box, and I'm going to use that. I'm going to use Newton's second law. It's a point mass, so we can apply directly Newton's second law. P dot equals 2F. I'm not talking about external forces, internal forces, because we have point mass, all forces are external, right? And, okay, so if I use this, immediately, our results which we are going to get at the end of this will be limited to what? The results will be limited to the inertial reference frame, because we are planning to use over here right now Newton's second law. Newton's second law works only in this form. In this form, of course, works only in inertial reference frames. So if we're over here planning to use Newton's second law, it means that the result will be limited to only inertial reference frames, right? So it means that, okay, let me remind. So it means that the result will be limited to inertial reference frames. So over here I can write inertial. Okay, so as a result, we're getting R cross F. Right. Okay, so now we're getting a new construction which we've never seen again in the development of Newtonian formalism, right? In this course, of course, you know all this, but we're developing this castle, Newtonian formalism castle, from scratch, from the foundation. So, and now it's the first time we see this construction. Let's give it a cool name, torque. Right. Or maybe I can still, no, let me write it there. So R cross F. All right, so let's gamma capital. So it's R cross F. And of course, that is the torque. Right. Again, torque, since there is R, again, sensitive to the position of the origin. Again, you can, as you move, if you start moving the origin, the value of the torque, you can make torque anything you want, right? So, definition of torque, again, I can even put 3 lines, basically, by definitions. All right, torque about this origin, let's call it point O. Right. And as a result, we're getting basically what is called rotational Newton's second law. Of course, right now written for a point mass. Right. Another red frame. Right. Okay, rotational Newton's second law. So we can call it rotational Newton second law. Okay, so we're getting something new where we introduce new quantity, right? And now, again, it's an attempt to describe a rotational motion. So after this, yeah, that's what I was planning to describe here. And now let's kind of digress. Because again, the next natural step should be what? We applied all this for a single particle. Of course, next step should be, let's move to a multi-particle system. But let's just pause for a second, right? And apply this for a particular system. Let's just basically derive Kepler's second law. And in what I said, it sounds ridiculous, not ridiculous, it sounds controversial, right? I said, let's derive a law. It shouldn't sound like that, because a law, or the law is something which is fundamental, right? Something fundamental cannot be derived. A law cannot be derived. So it means that although we call Kepler's laws as laws, but in reality they are not laws, because we can easily derive them from something which is more fundamental. And right now we are going to derive Kepler's second law. We call them laws basically out of respect to the history, right, to that great achievements, right. Of course, back then when they were founding them, when they found them, they saw that something fundamental, something, right, and they call them laws. But of course, now we all know that they are not laws, right? Since they can be derived using Newton's second law, right? But still, force of habit, we call them laws. So let's derive Kepler's second law. Let's just quickly refresh Kepler's laws. We are going to derive them all, but first, Kepler's second law. Kepler's first law, just refreshing. It's a planet, okay, the Earth moves around the sun following elliptical orbit. We are going to prove that. But of course, right now, we're not ready at all. And the proof is not that trivial, right? Although it sounds simple, right? Elliptical orbit, right? we'll have to sweat a lot in order to prove that. So position vector. As position vector moves, of course, it sweeps out some areas. And the areal velocities are the same. Basically, area which is swept by the position vector over here, for example, over a period of time delta t, will be exactly the same as when the planet is over here, right? And the area swept by the position vector over the same period of time delta t will be exactly the same. So basically, areal velocity is constant. So that's what we are going to prove now. And of course, the third law, again, we will prove it after the first law. It tells us that the square of the period is proportional to the cube of a semi-major axis, right? So again, we will prove it maybe in a few weeks. But now, Kepler's second law. All right, so it will take us probably 10-15 minutes to prove it. Kepler's, which way? Yeah. Second law. Okay, so what I probably should write something. A line drawn from the planet to the sun sweeps out equal areas. Okay, let me just use my notes. Right. So a line drawn which way? From the planet from a planet. Let me use a planet because it can be applied for any planet. From a planet to the sun sweeps out equal areas. Right, so that's the law. Again, every time when I pronounce it, laws, I feel kind of guilty, right, of lying. Right, okay, let me just sketch the situation. So what are we talking about? So I will start with the elliptical orbit. Let's say here's the sun. And if the Earth is here, okay, let me use some different color maybe. So if the Earth is in this part of the curve, and let's say over the period of time delta t, the Earth moves from this point to that point. So basically, this area sweeps out by the position vector r, right? Or if you look at when the Earth is here, right? So again, over the same period of time, this area will be exactly the same as that area. So areal velocities are the same. Right? So these are areas the same areas. Okay, so let's prove it. And of course, whenever you start solving a problem, of course, first of all, you need to make a decision about the reference frame. Where should you position the origin, right? And what, yeah, basically you make a decision about the reference frame. And of course, you know, I'm not going to ask you, right? So where should we position the origin and the reference frame? We all know, we've solved similar problems many times. And of course, every time the origin is at the sun. Why? So I will position, of course, origin at the sun. So this will be y-axis. This will be x-axis. But why? What's so special about this point? Right? Why we want to position origin over there? Of course, we're going to use this rotational Newton's second law. Right? So we're going to use L dot equals to the net torque acting on the system. The answer is more or less obvious. Why we position the origin at that point. Look at, you remember, I told you, and I emphasized on that. So the value of the angular momentum depends on the position of the origin. the value of torque also depends on the position of the origin through that r small. So it means that if you move the origin around, you can make torque anything. You can make L be anything, right? So if we position origin at the place of the sun, then we're dealing, okay, yeah, let's say I draw it here, right? So this is R, right? So let me look at this point, right? So when the sun, I mean, when the Earth is over here, so that is R, right? Forces are central. Force is central, right? So the force will be, of course, I didn't draw, no, I did draw. Right, so the force will be, okay, the force will be that way, towards the sun. Probably I should have drawn R underneath. Let me draw R over here. So this is R and that is F. So they are anti-parallel. And of course the torque will be equal to 0. So that's the beauty of positioning the origin at the sun. So the torque immediately is 0. And as a result, immediately angular momentum of the Earth will be conserved. That's the point. Otherwise, yeah, you could have positioned the origin over here, for example, make it inertial, right? Make it stationary, right? And again, it will be still correct, but of course your description would be significantly more complicated, right? Because then the right-hand side wouldn't be 0. Right? So positioning origin at the Earth, at the sun, simplifies the problem. All right, so the origin at the sun. So as a result, torque, which is R cross F, which we wrote, since F is central, then F is central. Since F is central, then of course it will be 0. Right? And as a result, immediately, of course, we're getting significant simplification of the problem. The angular momentum of the Earth is constant. Right? Okay, now knowing this fact, let's expand it and let's see where it will lead us. So L is a vector. L is constant as a vector, right? So it means what? So let me write underneath. L by definition, of course, it's a R cross P. And L is constant. So let me draw over here. Let's say this is my L. Wait, L small, right? This is my L, and it's constant. It means that magnitude is the same, and of course it doesn't wobble, right? So, and direction must be the same. And since L is the R cross P, and this is constant, it means that vector R and vector P must lie in the same plane. All the time you can find a plane, and R and P will be there. If they are not in the same plane, then L will start wobbling. But L is constant, we just showed that. So it means that it means that the motion is two-dimensional, right? That the Earth moves in the same plane every time you can find that plane, right? So it means that, okay, let me draw, let's assume that this is point, right? So this is R, this is P, right? And the lie in the same plane, right? Right. So R and P lie in the same plane. So it means that it's a two-dimensional motion. So it means that we have 2D motion, two-dimensional motion. Okay? And now, of course, it means that we can use, for example, polar coordinates to describe, which is much more convenient, right? But of course, first step, I needed this result. I needed to show that we have two-dimensional motion, and now let's switch to polar coordinates, right? So now let's go to polar coordinates. So basically, now I want to write L angular momentum in terms of polar coordinates. Right, you can make any transition, right? I will just outline quickly what I've done in my notes, right? Of course, x equals r cosine phi or theta, phi. Y equals r sine phi. Of course, you can differentiate in order to get x component of linear momentum, y component, or you can use just immediately write down the L determinant and open it up. It's up to you. So in my notes, I wrote this, right? So m x dot, right? So it will be m r dot cosine phi. Feel like I'm running out of space over there. R dot cosine phi, and then minus r phi dot sine phi. Right. And then of course will be similar for py, my dot, it will be m. Okay, it looks like I feel like I need to change the marker. So m r dot sine phi and plus r phi dot cosine phi. Okay, so now you can write a determinant, open it up, and you will end up with, or as I said, you could have written determinant immediately in polar coordinates, right? Dr. Egan carefully goes through usually that, right, in his review. He spent like almost a few weeks diligently reviewing all the vector calculus. Right, so of course now you can write L as R cross P, right? You can write a determinant, so which vectors I use I hat, j hat, k hat, and then x, y, and 0, because we have two-dimensional motion, and I oriented coordinate system so that motion happens in the xy plane. That's what we have here. So z in the axis, nothing happens in z direction. And then, of course, px, py, and of course 0, right? And if you open it up, of course I'm not going to do it, right? You will end up with, just simple massaging, you will end up with r squared phi dot m, and of course k hat direction. Of course, angular momentum will be, of course, in the perpendicular direction, in the z direction. Right? Okay, so that's what we want, and now, I need to erase this. These amazing features of the center of mass. Okay, I will erase it later. And so now let me write in the, not in the vector form, right? So I can write that phi dot equals to L divided by what? Mr squared. Mr squared. Okay, now let's leave it alone for a second. Okay, for a few minutes. We'll get back to this in a minute. And, right, so now let's look at, for example, this part of the trajectory. So I will draw it here. So let's say this is our trajectory. All right, so this is R, then over the period of time dt. Planet moves from this point to that point, and of course this will be d phi. Just a small portion of the trajectory. Right. And again, I want to look at the area because that's the goal. I want to see that the areal velocities are constant. And since this is an infinitesimally short period of time, infinitesimally small angle, right? So this real area which we have to count, I'm going to replace with approximately this. I will just draw a normal line, right? And I'm going to calculate this area. Right? So of course, this side is r d phi. This is r, right? From here to there, approximately. So just the area of a triangle, 1/2 base times height. Right, so let me call it dA. It will be 1/2 r times r d phi. So it will be 1/2 r squared d phi. So that's the area, approximately, of course, of that small area of that small area. Okay, but again, we want to look at the areal velocity. Okay, so let's just divide it by dt both sides. All right, of course, we're going to end up with dA over dt areal velocity, and over here, 1/2 r squared phi dot. So we introduce phi dot, and we have already prepared this ingredient prepared in advance. So we can plug it here. Of course, it will be r squared over 2 and L over m r squared. Of course, r squared gets cancelled, and we're getting that the areal velocity equals to L over 2m. And of course, since L is constant, angular momentum is constant, because we position the origin at this point, right? L is constant. And of course, absolute value of L is constant. So areal velocity is constant. Yeah, so we proved, right? So the areal velocity is constant, right? Yeah, although it's called a law, but again, it's just nothing to do with law, because we derived it, and it's basically it's just a fancy way of stating conservation of angular momentum, right? Over here at the very beginning, when we position the origin over there, angular momentum is constant, and of course we use some manipulation, some basically algebra, calculus, but from the physical point of view, we used only one fact: conservation of angular momentum. L is constant. And that fact that L is constant led us immediately to the sort of conservation of angular, conservation of areal velocity. Okay, areal velocity is constant. Sounds better. Okay, so just nothing then, just a fancy way of stating conservation of angular momentum. Right. So maybe let me write this. So it's just which way? A fancy way, or a fancy way of stating conservation of angular momentum. Conservation of angular momentum. Okay, now it's time to erase the rest. And okay, now the range of applicability of this Kepler's second law. Is it restricted to forces like gravitational force or electric force, or it has a larger validity? What are the restrictions? And we just need to look what we've used in order to get this result. Effectively, we haven't, not effectively, we haven't used, period, the expression for the force or potential, right? We haven't used the expression for the F or V, right? So it means that this result is not limited to the gravitational force or electric force, no. So what we've used, we used only one restriction on in terms of forces, right, or potentials. We used fact that F is central. So it means that this result is true for any central force, right? So you can take any force, and if any force, and if you see if it's central, you can say immediately, okay, so if something is going to orbit, right, so the areal velocity is going to be the same. Right? So for each Kepler's law, we're going to look at these limitations. In this case, it's correct for any central force. Right? And of course, also true for the force of gravity because it's central force. Electric force, it's central force, right? But you can come up with tons of central forces, right? Not just 1 over r squared forces. Okay, so when we derived all these 3 Kepler's laws, right, probably I will summarize these limitations. Right? But here, still, it's worth of mentioning. This law is true for any central force. Okay. This, okay, I will put in quotes law, because again, every time when I pronounce it, it makes me feel uncomfortable. This law is true for any central force. I think that's how I stated it. Yeah, is true for any central force. Okay, so I just after introduction of angular momentum, right, and this rotational Newton's second law, I just again wanted to emphasize on the fact that all this L and torque are sensitive to the position of origin. That's why I went into this derivation, because again, the key point that we position the origin at the position of the sun. And as a result, we tremendously simplify the description, right, of this system. Okay, and now let's go back to that. And so what's the next logical step, as I told you at the very beginning? The next logical step, let's move to a multi-particle system from one particle. Right. Okay, let me check if I mentioned everything. Yeah, it looks like. Right. So I guess I can continue here. No, I will start erasing this part because I will need plenty of room now. Right. So we're going to assume that we have n particles. Again, index alpha is going to, we will use to count all those particles. Again, there are some internal forces, of course, particles interacting, so there will be internal forces, and of course, there will be some external forces. All right. So the analysis will be similar to when we first time moved to a multi-particle system in the second class. All right, but now we have new tools, and now we want to look at multi-particle system using these tools, right? Angular momentum, torque, and rotational Newton's second law. So now we want to see what can we get out of that. Right. So now a new bullet. Get some water. So new big bullet. I feel like it's time also maybe change the marker, red one. It's as bad. Okay, I don't use it often, it should be enough. I will find a better one. So, multi-particle system. What do I need? Okay, I'll just let me draw them. These. Right, maybe more. Right, and then reference frame. Let's position it here. Probably I'm not going to impose restrictions immediately. Naturally, during the derivation, we will have to impose the fact that a reference frame must be inertial. Right? So for now, let it be like this. Right? So let's say this is our particle alpha, right? This one, right? And of course, it will be exposed to some external forces. So let's say this is my F alpha external. And of course, there will be internal forces. Right. Internal forces, let's say it will be over there. You know, it will be F on alpha from beta. And of course, yeah, position vector. Position vector. This, of course, R alpha, right? Okay. So how should I label it? Angular momentum for a multi-particle system. Let me label it. Angular momentum for a multi-particle system. Okay, so of course we will start with a single particle. Right. Alpha, of course, runs from 1 to n. Right, so angular momentum, the way we introduce it, R alpha cross P alpha, R alpha cross P alpha. And of course, since we have now plenty of particles, of course it makes sense. So let's look at the total angular momentum, which we labeled just L capital, right? L will be summation over L alpha. And of course, it will be summation over the whole system, R alpha cross P alpha, right? So the total angular momentum. Total angular momentum of the whole system. All right. So for now, we kind of, okay, so what a big deal. But in order to see the big deal, let's differentiate. Let's look at the dynamics of this angular momentum, total angular momentum of the system, dl over dt. Let's look at dynamics. So dl over dt. Okay, so now, of course, it will be summation over alpha from 1 to n, and is it true? Yeah. R alpha dot cross P alpha plus summation of R alpha cross P alpha dot. Again, like for a single particle, P alpha, it's a M alpha R alpha dot M alpha R alpha dot. So cross product of two vectors which are parallel to each other. Right. The difference only in the factor or in the mass. So of course this is 0. And over there, of course, I want to use Newton's second law. Rate of change of the linear momentum of a single particle, we can use Newton's second law. And of course, once we use that, the results are going to be restricted only to inertial reference frames. So now let's assume that our reference frame is inertial. So now, naturally, I want to use Newton's second law, and now, of course, I need to impose that restriction. So let's assume that this is inertial RF. You see, everything comes naturally. all the limitations. That's why it's good to know the derivations, right? So because in that case, you'll be comfortable and familiar with limits and applicabilities, range of applications, and so on. Right. So rate of change of the linear momentum equals to, again, now F alpha net force, all forces, internal, external, whatever, all the forces. Right, so Newton's second law, and again, once we use Newton's second law, it means that results will be restricted to inertial reference frames. Right, and as a result, we're getting, all right. Okay, not getting. I was just, let me rewrite it, and so it will be summation of R alpha cross F alpha. I guess my neighbors hate this because the wall is the whiteboard is attaching to the wall, and I keep writing, keep making this noise. All right. Okay. So again, inside of these forces, we can have internal and external forces. So let's sort them out. So F alpha equals F alpha external, and plus. Okay. Now we need to sum up all the internal forces because we have n particles, and so we need to sum. And summation will be over beta now. Beta from 1 to n. F on alpha comes from beta, right? But since particle cannot exert force on itself, we have to exclude alpha from this summation. It's sort of like particle cannot exert force on itself. It's only possible, probably you've heard that German story about Baron Munchausen, right? Who managed to pull himself and his horse out of the swamp by pulling his hair up, right? So basically that's the story, right? Particle cannot exert force on itself. It's only in the fairy tales, right? In German fairy tales. So, I said that, but I didn't write it. So beta is not equals to alpha. Particle cannot exert force on itself. Right, and of course, now we will have two summations, two sums. So first one is simple, alpha 1 to n, R alpha crossed with external forces. F alpha external. So nothing can be done with this, right? So meaning of this quite straightforward. It's just a net external torque acting on the whole system. So nothing complicated. But the second term, summation over alpha, summation over beta, and R alpha cross those internal forces, right? R alpha crossed with F alpha beta, right? Okay, that term we have to look carefully. We've done something similar again when we first time started looking at multi-particle systems, but of course we did not have these tools. We just looked at the rate of change of the total linear momentum. Now we're looking at the rate of change of the total angular momentum, but plenty of steps are very similar. Okay, so now we need to manipulate that, and I feel like trying to estimate, should I continue writing here or should I jump on the next? All right. Okay, I will try to squeeze here. I will probably do this. I will take this summation, and I just don't want to rewrite that long term, big term again, right? So I will continue there. I just want to look at that term separately. Right, okay, so now instead of two sums, I will just use one and double sum, summation over alpha and beta. And I'm going to add exactly the same terms. So R alpha cross F alpha beta, and then plus R alpha cross R F alpha beta. And then, of course, divide by 2. Right, so I'm going to do this, right? So 1 over 2, and R alpha cross F alpha beta plus R alpha cross F alpha beta. So I double number of terms and divide it by 2. Okay, so far it's not a crime, mathematical crime. Now, in the second sum, again, as I said, similar steps to what we've done in the second class, I think. Dummy indices, alpha and beta, they don't go outside of that sum. So it means that you can do whatever you feel like doing with their names. You can call them Paul and John, right? Or you can switch alpha to beta and beta to alpha. We've done that, and now let's do it one more time. Let's just, in the second sum over here, interchange alphas and betas. Minor compulsion. Right, so only over here, right, alpha will be called beta and beta will be called alpha. And of course, now we need to impose additional restriction. We're going to use, of course, Newton's third law. So we're going to assume that internal forces obey Newton's third law. Right, so it means that F, okay, now I'm going to get, of course, F beta alpha. So let me write F beta alpha equals to minus F alpha beta. So we're going to make that assumption. Right, and again, it means that our result will be limited to a multi-particle system if their internal forces obey Newton's third law. Right, so we keep imposing additional restrictions. Right? Now, I have to move to this side. Right, so we'll continue that. It will be equal 1 over 2 summation over alpha and beta. Here I'm going to have minus F alpha beta. Right? So it means that F alpha beta over here and F alpha beta can be factored out. And I'm going to get R alpha minus R beta, because this alpha will be beta. So it will be R alpha minus R beta and crossed with F alpha beta. Again, that minus, and here it's R beta and F alpha beta. Damn it, right? It looks like after these transformations in the second class, we managed to make the term 0. But now, it's still not 0. That cross product, there are no any reasons to call that. There are no any reasons to call that term is 0. So let me look at these particles alpha and beta in order to understand what else can be imposed in order to make that term 0. Which one? Here, let's say this is my beta particle. Let's say this is alpha particle, and that is the origin. Let me make it over here. Right. So this is R beta. This is R alpha. Okay, my R beta looks ugly. R beta, right? And of course, this will be, okay, let me use some different color. This will be what? R alpha minus R beta, right? So that vector. Is it true? Yeah, if I add them, I'll get R alpha. Yeah, so that's the correct difference. And now, in order to make this 0, we have to impose additional, we have to assume additional thing. If we assume that these forces are central, it means that they will act along the line connecting these two particles. And in this case, this vector and this vector, they can be either parallel or anti-parallel, right? And that cross product is 0. So we have to impose additional restrictions. So internal forces acting between those particles must be central. And again, for most of these systems, for plenty of systems, right, it's true. Especially if the forces are, for example, gravitational forces or electrical forces. That's what most of the time we have, right? So all these results will be applicable for those systems. So we imposed, right, Newton's second law. As a result, the result of all this can be used only in the inertial reference frame. Then we imposed Newton's third law. Actually, I didn't write it, and I feel it's not right. So we imposed that. And now we're imposing additional condition. We assume that internal forces are central. So let me emphasize. So that is the first condition. This is the second condition. And now the third one. So let's assume F alpha betas are central. Again, in the second class, we didn't have to make this assumption in order to prove that internal forces cancel each other out. Now we have to make this assumption. So as a result, equals to 0. So we're going to make that assumption over here. So the cross product is 0. So as a result, this is 0. And what's left, again, what we're looking at the dynamics of the total angular momentum of the whole multi-particle system. So we're getting, which way I wrote L dot or this, just a second. Yeah, L dot. Let me write L dot. So L dot equals to this, that summation over alpha from 1 to n, and that is R alpha cross F alpha external. So basically, that is the net external torque acting on the whole system. So it will be L dot equals to gamma upper script, yeah, external, right? Okay, and again, it's not strictly speaking rotational Newton's second law. Rotational Newton's second law we introduced for a single particle. That's basically a Newton's second law, rotational Newton's second law, adopted for a multi-particle system. Of course, making these assumptions, right? So internal forces are central, and internal forces are based Newton's third law. Only under those conditions, under those assumptions, that is correct, right? So. Okay, let me write something. So it's a rotational Newton second law applied for a multi-particle system. Applied for a multi-particle system. Because again, Newton's second laws, rotational or translational, they introduced for point masses, right, for a single particle. Right, okay, and now, so what's the, what are the beauties, advantages, right, consequences of this? Internal forces, again, got washed out, right? They cancel each other out. Or not internal torques, not forces, internal torques. They cancel each other out. Again, what it means, so here is, what can be used? I can use probably this, my mark. So I have this ball, right? right now it's not spinning, right? So it means that what's the total, it's a multi-particle system effectively, right? So it means that the total angular momentum is right now 0, right? Total angular momentum is 0. You know what, before I start discussing this, right? So what I said is absolutely correct, but before that. All right, so basically it means that internal torques are not capable of changing the total angular momentum of the system. If you want to change total angular momentum, you have to apply external torques only, right? And now back to my example, just I should have mentioned it before. All right, so right now angular momentum is 0, total angular momentum of this multi-particle system. And of course, if I don't apply external torques, the angular momentum is not going to change. It is not going to start spinning by itself because of the internal torques. Internal torques, they cancel each other out brutally, right? Internal torques are not capable of doing this. Of course, if they manage to start spinning this ball, of course, it will scare, the living day out of me, right? And of course, then we will get the Nobel Prize for observing something tremendous, significant, important, absolutely new, right? Okay, it's, as I said, similar discussions. Discussions are similar to the ones which we had in the second or third class, right, when we discussed multi-particle system using the tools of linear momentum, right? Yeah. And then, of course, what's the role of these internal torques? Okay, they cannot change the total angular momentum of the system. Only external torques can do that. So what's the role of the internal torques? They allow us to, or they redistribute the angular momentum, the total angular momentum within the system, right? So you can have multi-particle system. So first, most of the angular momentum can be in this part of the system. But because of these internal torques, angular momentum can move to this part of the system or that part, or they can redistribute the total angular momentum kind of uniformly over the system, right? So that's the job of internal torques, redistribution of the angular momentum. Right? But of course, they cannot change the total angular momentum. So while redistributing, the total angular momentum stays the same, right? Unless there are external torques, and then of course that total angular momentum can go up or down. As I said, it's sort of the role of these internal torques or internal forces similar to the role of government in the country. Government is not supposed to make money. It's not supposed, right? Their role is to collect taxes, right, and then redistribute, right? So the total wealth of the country stays the same. They just redistribute money. So you are good, here's some money for you. You are bad, you're not going to get something, right? And only external forces, right? Some companies working with some foreign companies can make money, right? Bring more wealth to the country, right? Something like this. All right. Okay, so let me think what, to make sure that I've mentioned everything which I was planning. Actually, the time is almost up. All right, okay, so direct consequence. So if net external torque acting on the system is 0, then the corresponding angular momentum, total angular momentum, of course, is conserved, right? So we're getting conservation of angular momentum, right? So important consequence. So if net okay, I used upper script, external torque equals 0, then of course the angular momentum is constant. So L is constant. Conservation of angular momentum. Conservation of angular momentum. Oops. And of course, it can be conservation of angular momentum over a certain direction. It can be only in z direction. If net external torque in z direction is 0, then angular momentum in that direction will be constant, right? All right, and again, all right, so this is basically like an alphabet, right? So if somebody wakes you up in the middle of the night, you should be able to answer, right? So under which conditions angular momentum is conserved? Because very often on the qualifier exam, you can hear something very strange, right? Again, it's sort of, when is linear momentum conserved? When net external force equals 0. When is angular momentum conserved? When the net external torque equals to 0, right? All right, yeah, yeah, the time is up. So I thought moving slightly deeper. Okay, so what are we going to do after this? Right? Again, we just introduced a new set of tools, and we played with them, right? First for a single particle, now for a multi-particle system. But still, we didn't see the whole beauty. Actually, this is the universal law which describes multi-particle system. Yeah, it's, no, what I'm trying to make the point. You remember that center of mass point simplified description of multi-particle system significantly. And now, let's try to apply again center of mass point into all this mass. Are we going to get some simplifications again in this, in the description of rotational motion, right? So next class, we will spend maybe like 15-20 minutes diving into that. So we will introduce now the center of mass somewhere in the middle of these points. In the middle of the system, there will be center of mass. So we will rewrite these equations, right? L and gamma, including the center of mass, hoping to get something interesting, useful, and again, the most important, can we simplify a life in terms of calculations, right? And of course, center of mass, even in this case, is very important, right? Okay, so next class we will include center of mass into this mass, right? And I guess after that, I need to look carefully, right? I think it's time to start looking at examples. We haven't looked at examples for 3, I think, or 2.5, 3 classes, because we keep developing introducing new tools and developing procedures, right? Because most of the system, it's a superposition of sort of translational and rotational motion. And of course, we need the previous results as well as these new results in order to describe, for example, the motion of this ball, right? So it's a translational motion plus rotational motion. So we cannot use just the previous results from the previous class, because if we start applying only those results, problems will be ridiculously simple. Right? So we need to, of course, superimpose translational and rotational motion. So we need to finish developing this box of